You, Bill.
I see your screen, but I don't hear any audio.
Bill is muted at this time.
And thank you. I will solve that problem right away. Very good. So today we're going to talk about simple sorts. A good starting point in fourth and code that will be done in a couple of words. So I developed a matrix computation system a couple of years ago, continuing to refine it. I'm on like fifth generation by now. And I needed a simple sort, mostly for demonstration, mostly for learning. The sort from 10 to 100 rows matrix, and something in that range. And I'm using the simple bubble sort here, but as we know, more complex sorts are suitable for larger matrices. We'll talk about performance in a few moments. So for the beginning bubble sort, there are four basic strategies, at least I came on. The first one is to do a full sort of all rows. If you have a 10-row matrix, you sort over 9 rows, and the time is n squared because you are having to sort a 10-row matrix 10 times. So you can improve that slightly by using an early exit, because if the matrix is partially sorted ahead of time, if there is some early ordering, you will get done in less than n squared passes, and therefore you can make an early exit, and it will make a small improvement. A diminishing sort. In the case of a bubble sort, when you sort from row 1 down to row 9 on a 10-row sort, the last row, the 10th row, will be absolutely the highest or the greatest value that you found. So there's no need to sort that 10th row again. So the next time you can sort down through 0 through 9, then 0 through 8, 7, 6, 5, 4, down to the final sort, which would be on row 1 and 2. So a diminishing sort gets you to n squared divided by 2, which is a 2 to 1 time improvement, which is significant. And then you can use a diminishing sort with an early exit, which would make a statistically a very small improvement, potentially improvement. So when do we use bubble sorts? Well, there actually is a practical use for bubble sorts. If you're using an insertion sort, in this case, you create a target matrix and you sort into the target matrix, placing the rows at approximately the point where you think they're going to end up. At the end, you will end up with your rows some number away from ideal, maybe 2, 3, 4, 5, 6 rows from ideal. So in that case, you then run a bubble sort until you have no more row swaps. And if your rows are within 5 rows of theoretical, then you only have to sort through 5 times. Now, if you're on a 10,000 matrix sort, you do your insertion sort, and then out of a 10,000 row matrix, you only have to sort 5 times. And so that's a trivial time compared to, say, 10,000 rows. So the bubble sort does have its uses. As we see, the time sort increases by n squared. As you add, if you add 10 times the rows, you're going to have 100 times the sort time. Every time you add a digit to the number of rows, that is going from 10 to 100, your sort time goes up by 100-fold. And one of the nicest parts of this, especially for my work, is you can sort in place. You need almost no temporary memory. And the only temporary memory you need is for a buffer to hold one complete row. So on the fly, you can create a buffer for one row and then sort in place. We go downward scan row by row by row, examining a count value. If the column entry is larger than the next column entry, then you exchange the rows. And so the smaller numbers bubble to the top, the larger numbers bubble to the bottom. And a real advantage of this is that you preserve the order of prior sorted columns. We'll see that later. So if you're sorting on 2 or 3 columns, the subcolumns in each group will maintain their original order. And this is quite valuable when you're sorting databases. And as I said, each scan can cover one less row as the prior. So here's an example. This is a 3 by 10 matrix, 3 columns by 10 rows. And you see they're all random numbers. This is all floating point. So these are floating point numbers, although I've limited them to be integers for clarity. So here's our sort on column number 3. As you see we go 1, 2, 2, 4, 4, 5, 6, 2 sevens, and a 9. Then repeating the sort on column 3 and then 2, we now see that column 2 is in order. And if you look down column 3, down at the bottom for 8, the row that has a leading 8 has a third column 4, followed by a 7 by a 9. So you see that within the 2-column 8 results, the third column is maintaining as an order. This is particularly useful if you're sorting alphabetized lists, because you're keeping things in alphabetic order. You could be sorting by last name and then by sorting by first name, and so it maintains a reasonable usefulness. So here's our code. The row exchange is where we spend most of the computing time. In this case, the first sequence of the 3-pick, 2-pick, and so on takes the first row and copies it into the transient buffer. The second row takes the second row of our matrix, moves it to the first position. In other words, we've now done a transfer from the lower to the higher value. And then finally, the third section of the code goes back to transient and then puts the transient value into the lower row. So we go upper to transient, lower to upper, and then transient to lower. If you spend any time optimizing code, this is the place where you optimize, because this is executed for every single row, every single time. This is the code to do one pass through the matrix. At the input, we give it the X curly brace is the specifier for our source matrix. C is the column we're going to search on, and then row through gives us the ending row. So we always start at the initial row, and we'll sort down through that through row. So this allows us to adaptively change the depth into which we're going to sort the matrix. So in this case, we pick the first the ith cell, and then we take the ith plus 1 cell. F greater than compares the two floating point numbers. If the second number is larger than the first, the green row exchange will swap the two rows. So I would guess statistically this the row exchange will occur about half the time. And finally, this is the outer wrapper around the whole thing, bubble sort. In this case, we give it the X curly brace give us the matrix. Column is the column number we wish to sort on. And then first step is we open up a transient matrix, which is simply one row. So the 1, 2-pick number of columns, open transient, opens up a transient row, which is all of the columns wide. Then we determine the number of rows in the matrix, and then under the do I is to pick the first row we're going to sort on, and we do one pass, and then sort repeated, then decrement by the loop by 1, and do it the second pass. So in this case, we start out at the first time is on the 9th row, work back to the 8th, 7th, 6th, 5, and we get back to row 0, we're done. And then at the bottom, we drop a couple of parameters and close the transient buffer. So here's our results. In this example of a 3x10, the what I'm calling square matrix is where we sort all rows every time. And so it's less than 1 millisecond for 10, or a 10 row sort, about 40 milliseconds. For a 1,000 row sort, about 4 seconds. And we'll see the 10,000 row in a moment. This is the same sort with an early exit, and you see there is a very slight improvement, and this is statistical. It only depends if the matrix is done sorting early. It'll cut down the sort time slightly. So we go from the 10 row goes from 40 milliseconds to 34, and the 1,000 row matrix goes from 4.4 seconds to 3.7 seconds, just as we would expect. This is the decreasing sort. And in this case, of course, it's less than 1 millisecond for 10. For a 100 row, it's 32 milliseconds. I expected a little better improvement than that, but that's the way it turned out. So there is some overhead in there. I expected a greater improvement, but I didn't get it. The 1,000 row sort goes to 3.8 seconds, which is shorter than the square, but slightly longer than the square with an early exit. And finally, the 10,000 row shows you this n squared penalty, because I did it a couple of times, and one time the sort took 5 minutes 29 seconds, the next time was 6 minutes 41 seconds. And if you look at 3.8 seconds squared is about the 10 squared is 100 times longer, and it's about 40 seconds, and that works out to be about 5 minutes. And finally, the decreasing sort with the early exit, again, makes a slight improvement. It's random, because statistical rather, so that at a 100 row matrix, the fastest time was in 16 milliseconds, and the slowest was 32. So if it finds a partially supported matrix, it may terminate early. And finally, on the 1,000 row, we got down to as low as 2.3 seconds. So onward. Well, if I'm doing true production work, I have some projects involved where the sorts would be in the range of the low thousands, 1, 2, 3,000. I definitely should move to a more complex sort. The candidates would be a shell sort or insertion sort, which are classics. And I will compliment Microsoft that the sorts in Excel are fantastic. I am currently doing work on spreadsheets, and I'm doing 1,000 row, 2,000 row sorts routinely, and the results appear to be almost instantaneous. I mean, it's maybe a few tenths of a second. So whatever they're doing, it's fantastic. And I suspect they use large amounts of short-term memory. In other words, they are certainly not sorting in place, but they are probably using a couple of different buffers to optimize this sort process. And that is my conclusion. Do we have any requests or comments?
Anyone try something like radix sort, which is probably used for things like chromosomes? Radix sort is supposed to be fast, but in theory and practice,
Well, I'm certainly not one to comment on the relative performance of them. I have The Art of Computer Programming by Don Knuth, and that is my go-to source on it. And he's got all of them in the book up to quicksort. And so I think my next approach is going to be an insertion sort. In this case, we just create a large duplicate buffer and sort into that buffer, and then with insertion sort, and then do a bubble sort to end with. Any other comments? Yes.
Sorting is something that I'm not happy with, because it's not a stable sort. And Cozy, that's a name. If things are equal, the sort does not change the order. So I need to go to some stable sort. But one comment, in APL, it's rather interesting that the only instruction goes and returns the permutation vector for the sort. And I've implemented that in Cozy so that when you have multiple columns and they may be mixed alphabetic and and numeric, essentially when you sort on a column, it returns the sort permutation. So then you can apply that to all the rest of the table. And so actually in Cozy, because I don't know any way to get the permutation without doing the sort, I return both. But that's very useful, but I don't have a stable sort. And that's a major problem. That's a major issue.
Yes. I'm looking at the comments to see if there's any comments that apply. Several comments in here. I suggest you all read through there. They're provocative on chromosomes and DNA. And here's the Tim sort. Oh, everybody seems to be using Tim sort. So Brad suggests that. I will look that up. No further comments. Thank you. We'll return to Fearless Leader. Kevin, take it away. Thank you.
All right. Thank you, Bill.